In this video, we're going to look at the Arrhenius equation, which tells us how the rate constant depends on temperature. And so in this example, we're looking at the decomposition of ozone, and we want to determine the activation energy and the frequency factor. And we're given a bunch of temperatures and the rate constant at those temperatures. So it's the Arrhenius equation that tells us how the rate constant depends on temperature. And one form of the Arrhenius equation is that the rate constant is equal to A, which is the frequency factor, times E raised to the power the negative of the activation energy divided by the gas constant times temperature. Now in class, I showed you how to rearrange the Arrhenius equation to have the form below. And the reason I show this form of the Arrhenius equation is because if I plot the natural log of the rate constant versus the inverse of the temperature, I will get a straight line. And the slope of that line will be negative EA over R, and the y-intercept of that line will be the natural log of the frequency factor. So I can use the data that I had on the previous slide, make a plot of the natural log of the rate constant versus 1 over the temperature, and that will allow me to determine the activation energy and the frequency factor. So let's go to Microsoft Excel. All right, so I've gone ahead and typed in the data from the PowerPoint slide, but I don't want to plot the rate constant versus temperature. I want to plot the rate constant, or the natural log of the rate constant, versus the inverse of the temperature. So I need to manipulate my data a little bit. And remember that whenever you're making a plot in Excel, the X variable needs to be in the left-hand column and the Y variable needs to be in the right-hand column. So if I want the inverse of the temperature, I could get out my calculator and do 1 over 600 and 1 over 700, and that would be fine, but it would take a while. It's much easier to have Excel do it for me. So I'm going to enter an equation, and to tell Excel it's an equation, I'll type equals, and I'll do 1 over, and then click on the cell that I want to take the inverse of. So I want the inverse of the temperature, and then hit enter. I don't have to keep retyping that equation into all these cells. I can just copy and paste it. So I'll copy my formula with right-click, and then I'll highlight the cells I want to paste it into, and right-click, paste. So now I have all my inverse temperatures. Now I want to take the natural log of the rate constant. So I'll enter another formula, so it's equals, and then ln for natural log, open the parentheses, click on the cell that I want to take the natural log of, close the parentheses, enter, and then I'll copy that formula and paste it into the cells. So right-click, copy, highlight the cells, right-click, paste. And I should have said one thing before when I was showing you the data. To enter data in scientific notation in Excel, you want to use E, right? So the number that I wanted to enter is 3.37 times 10 to the third. So in Excel, I typed 3.37 E3. Okay, back to the data on the right here. So I've got 1 over temperature as my X variable. I've got the natural log of the rate constant as my Y variable. So now I want to plot these, so I'll highlight them. All right, and so on a Mac, I'll click on the Charts button up here. On a PC, there's probably an Insert button, depending on the version of Excel that you're doing. You want to insert a chart. Remember that whenever we're doing a plot of Y versus X, I don't want to do the line plot. I always want to choose the scatter. So I'll go down here to Other, and I'll just do the marked scatter. And so here's my graph. And remember that in order to determine the activation energy and the frequency factor, I want to get the slope and intercept of the line. So I need to add a trend line. So I'll click on the data and then right-click on one of the data points. Go down to Add Trend Line. You want to be sure to click on the Options tab and then display the equation on the chart. I'll go ahead and display the R² value. If you're on a PC, your window will look a little bit different, but you want to find the options for displaying the equation on the chart and displaying the R² value. Click on OK. So here's my equation. So now I can use the equation that from the graph to find the activation energy and the frequency factor. So let's go back to PowerPoint. All right, so remember, the slope of the line is going to be minus EA over R. sorry, the slope is going to of the line is going to be equal to minus EA over R, and the y-intercept B is going to be the natural log of A. All right, so first let's find the activation energy. So as we said, the slope is going to be minus EA over R. Here's the equation of the line from Excel. And so to rearrange this, right, I'll multiply both sides by R, multiply both sides by minus 1. So the activation energy is the negative of the slope times R. So the slope is negative 11175. And the units, remember the units are the units on the Y divided by the units on the X. So the reason the units are Kelvin is because we plotted the natural log of the rate constant on the y-axis. And when I do the natural log, essentially that kills the units. So there's no units on the y-axis. The x-axis was 1 over temperature. So because the units on the slope are going to be y over x, I'm going to have 1 over Kelvin. So that comes out to be Kelvin. And then I have the gas constant is 8.315, and the units are joules per mole dot Kelvin. So when I multiply these out, right, the negative times a negative becomes a positive. And then for the units, the Kelvin here cancels with the Kelvin in the denominator. And so my answer is the activation energy is 92,900 joules per mole, or to convert that to kilojoules per mole, it would be 92.9 kilojoules per mole. All right, and then the last thing we have to do is get the frequency factor. So we know that the y-intercept is going to be equal to the frequency factor. So here's the y-intercept. So the natural log of A is equal to the y-intercept. To solve for A, to get rid of the natural log, I'll raise e to both sides. So I've got e to the natural log of A is equal to e to 26.576. E to the ln of A is just A. That's how we got rid of the natural log. And then e to the 26.56 is 3.48 times 10 to the 11. Now the units are not really able to figure those out from the graph. Remember that the units on the frequency factor will always be the same as the units on the rate constant. So because our rate constant was given units of molarity to the -1, seconds to the -1, if you go back to the beginning of the video, you can see the table that had the units. And so those are the same units that the frequency factor will have.